Okay, good morning, everyone. Hope everyone had a nice weekend. Top hat code for today is 2691. Just a reminder that assignment number 3 on matrix multiplication, comparing 3 algorithms, is due today. Was extended from yesterday. One algorithm is just using the built-in or semi-built-in algorithm that is provided by NP, NumPy, or the equivalent if you're using another language, some built-in library, then coding it yourself the way you would do it from a linear algebra class. And finally, the matrix, the Strawson's matrix divide and conquer matrix multiplication algorithm. I know some of you encountered some kind of issue with tuples and slices. If you still have that issue, we can stay on at the end of class and we can address it that way. I tried to give you some ideas in the Slack, but if you still have that issue, we can take a look at that at the end of class. Okay, I did assign assignment number 4. Assignment number 4, you have a choice of 2 different assignments. One of them is to do a study of hashing hash tables, different collision resolution strategies. And the other is, if you prefer trees, you're into nature, you can do computer science trees. All right, so both of those are search mechanisms. So in a sense, they are related, but instead of having to do all of it, so you can choose either 4 of the hash or 4 of the tree. And I give you some more specific suggestions here. Just a reminder, so in general, I would say that most people in the class, 90% of the people in the class, are working within the template from assignment number 1 that we developed together. I think some people are sort of veering from that. And when you veer from that, a number of things happen. One of them is you land up your format. So it becomes harder to do the graph because you're no longer following that format. Your table is no longer a table. You just have print statements all over the place. And you end up, even if it looks good, you tend to have more code because you're doing everything not in the sort of streamlined kind of way. So I would encourage everyone to work within that template. If you are programming in Java, I think most of you are sticking with the Python, but you can use a similar template. You can do things with what's called reflection to iterate over a number of names of functions or other ways of doing it. So I really encourage you to work within that template and do that for assignment number 4. Right, assignment number 4, you're going to have 4 different hash tables that you're going to work with, or 4 different trees. But again, you're going to be looping over a number of numbers that you need to look up, and then you iterate over the data structures and you pass in the data structure that you're looking at. Okay, so with that, today is going to be sort of a survey. I wouldn't say it's a in-depth study. It's more of a survey of tree and heap structures that are out there. So we will talk about the familiar heap and the familiar heap, and then trees, and then the less familiar ones. Some of this you will have seen data structures, and some of it maybe not. All right. So first of all, let's just review the definition of a tree. So a tree in this context. Okay. So in my 220 class, we'll define tree a little bit differently. But in this context, it's an abstract data type. An abstract data type means we don't necessarily know what the implementation is going to be. It's a hierarchical structure as opposed to what would be like the opposite of hierarchical. And you can write it in the chat if you like. So flat, or a list, right? An array is just a plain flat structure. Okay, so the nodes are connected to each other, and a node could be connected to many children, but it should have only one parent. All right, there are ideas of inverted trees where the root is on the bottom. We're not going to talk about that today. Okay, so that's a tree. And then we have a heap. A heap is also a kind of tree structure. However, it has a certain property, and that is it's generally either a max heap or a min heap. So in the max heap, the largest number is going to be in the root. Its children will be less than that, and each of its respective children will be less than whatever's at the parent. And in a mini, it's the other way around, right? So the parent has the smallest value, and its children are going to be larger than that, and each of those nodes' children in turn will have children that are larger than it, right? So that's a heap, all right? And typically when you learn about trees and heaps, you start with binary trees or binary heaps, which means that each node will have at most 2, and in the case of a heap, generally that means usually 2, the certain exceptions at the end. And in a binary tree, not so much, right? It's very possible that you have a lot of things without that in addition. Okay, so I have a bunch of terminology here. So I'm not going to go through everything here, just I don't know, one thing I don't have. You know what I don't have here? I don't have the height. Okay, so let's, why don't we add height ourselves? So what is the height? How would you define the height of a tree?
From the root to the lowest node.
Yeah, I'm surprised. How did I lose that? Okay, so we'll say that. So we'll say the height. Okay, so the height is the distance from the root to the furthest. Okay, so maximum. Let's tell us that as well. Okay, just one thing to keep in mind is that, okay, what level, if you will, is the root? Okay, because sometimes people count differently. So let's just make sure that at least we're on the same page for our purposes here.
0.
0. All right. So if you have a full tree with 3 nodes, right? So that's going to be of height 1, right? 0, 1, and 1. Okay, we have some special trees here. Okay, so we have binary trees that agree with degree 2. That means that each node can have at most 2 vertices. A ternary tree has degree 3. That means each vertex can have it, or node can have at most 3 children. And an n-ary tree has degree n. Or okay, maybe we'll change that to m, because n is usually by convention the number of nodes in the tree. So we're going to change that to a m-ary. Okay, not to be confused with Mary. Okay, we have a full binary tree. So here we have some terminology that is sometimes confused. Okay, so every non-leaf node has 2 children. Okay, or we can have a complete binary tree where everything is completely filled and the nodes are as far left as possible. Okay, so how are the full and the complete different?
With the full, the leaf could potentially have 1 child as long as it's the leftmost one.
Okay, so for example, let's say you have a binary tree and the left side is very congested, okay, many layers there, and the right side has 1 node. Okay, so as far as the root is concerned, the root has 2 children, right? So in that sense, it obeys the rules of full binary tree, right? So the left and the right are both populated, so it has 2 children. Now that child on the right-hand side has no children. It's a leaf. So in that sense, as long as the left-hand side is full, right, the right-hand side has met its requirement. It's a leaf. It doesn't have to have any children. That would not be consistent with a complete binary tree, because in a complete binary tree, every row has to be filled in except possibly the last. And we see that, by the way, in a heap, right? So a heap is going to be complete. All right, another term that is going to be very important in our not only today, but also later on when we use these trees for various purposes. It's concept of a balanced binary tree, right? So in loosely speaking, balanced binary tree means the left and the right are roughly the same. Okay, but we can define roughly the same a little bit more scientifically, and it means that if I take any left and right subtree, right? So for any given node, I look at the subtree, right? Whatever I have on the left, whatever on the right, I calculate their height. You can do a recursive function for that, and I take the difference, and it's going to be less than or equal to 1, right? We also have a forest. Now, a forest is a set of trees, all right? So technically, it's not a tree because a tree has to be connected. That's an important definition. And a tree also needs to be cycle-free, okay, or what we call acyclic. So technically speaking, a forest really isn't a tree. It's a set of trees, and they need to be disjoint, okay? Disjoint is a fancy mathematical term. That means not overlapping, right? So they don't share any nodes, they don't share any edges, all right? But it's associated with trees because it's a set of trees, and therefore it's usually discussed in this context, right? Later on today, when we talk about certain heaps, we'll see something like a forest. Maybe it's not exactly like a forest, but it's similar. Okay, and then we have an order tree, all right? So an order tree is just a general term that means that there's some kind of ordering, you know, of the children relative to the root. Now, a tree does not have to be ordered. It's possible to just put things in at random, okay? Just another way of storing that. Now, how are you going to find things? Okay, that's another story, but it is an option. Okay, sometimes the information about how they're stored may be elsewhere. Okay, so you may have some other information that tells you where you could look for something. Let's just come back to that for a second, right? So one of many areas where this is all relevant is networking, right? Networking, you have, you know, different things connected to each other. So a network is not necessarily a tree, right? Because you could have a cycle, for example, in a network where things are connected to each other in such a way that you can go around. A ring network is an example of that. A mesh network is an example of that. But it is possible to have what's called a star network. Is anyone familiar with what a star network looks like? It does not look like an American star. Anyone familiar with that? Well, some of you are in 355. Anybody? Star network? It looks sort of like an asterisk, right? You got something in the middle. Usually it's a server in the middle, and then you have all the devices off to the side. That's a kind of tree, right? But it's not particularly ordered. In other words, you know, there's no relationship, you know, the ones on the top are more than the ones off to the side, right? Why is it structured that way? Well, you can get from a server, let's say, quickly to any other node, provided that you know which one you want to go to. So the point here is it doesn't necessarily have to be ordered to be a valid tree structure, right? So these are some of the more specific ones. And again, I'm going to change that to M-ARY. All right, so we're going to start with our old faithful binary search tree, talk about what it is, we'll talk about some of the problems with it, and then we will provide some alternatives. So a binary search tree is not just a binary tree, but it's used for searching, which means that it should have some kind of order in it. It's a directed tree. What do I mean by directed tree? A directed tree means there's direction on the edges. So the trees that we'll be dealing with are mostly directed downward, right? So everything is in the direction of root to a lower level. Sometimes you can have trees that are directed in the other direction, but they all need to be in the same direction. Okay, it's a binary search tree, which means that each node has at most 2 children. The key and data are stored in the node. Okay, is that obvious? This point here, would you say that that's obvious? Are there other options? So, that's what we're used to. But when we get to B trees and B plus trees, we're going to see that the data generally isn't stored there. Okay, we have the keys that allow us to navigate down to the bottom of the tree, but the data is actually stored somewhere else. All right, so then we get to the BST property, if you will, right, that really characterizes it. So the rule is you have a particular node, so any key that is in the left subtree of that node is going to be smaller, and any one that is in the right subtree is going to be larger. Obviously, if we have a duplicate keys, which isn't necessarily such a good idea in a search context, but if you do have duplicate keys, then you have to decide what happens in the case of equality. Does it go to the left? Does it go to the right? Or can it go to either? Right? Either creates confusion, but that is a possibility. Right, how do we get the height of the tree? So the height of the tree is going to be 1 plus the height of the left and the right. Okay. Now, any recursion needs a base case. What do you think the base case should be?
There's only one node, it's height 0.
Yeah. So it should be defined as 0. When there are no nodes, we use -1. Okay, so if you try to code this, you'll see it gets a little tricky to make it work across the board. So the general case is sort of simple. That's something to watch out for. Okay, now we get to a little bit of the analysis part, which is what is the height? So if n is the number of nodes or the number of keys in the tree, so what is the height? And it's at most n minus 1, which means in asymptotic notation it's O of n. And why is that? Well, if you have like a snake-like pattern, right? They all go straight down to the right or straight down to the left, or even if they weave back and forth, as long as you're never really getting 2 children. So the number of nodes along that path is n, and the number of edges in between those nodes is n minus 1. However, on average, well, let's lower bound it first. So lower bound means that every node has 2 children, except if it's a leaf where it can't go any further, right? So that's going to give us log of n. And actually, that combined with it being complete will give us log of n. What about the average? So maybe I should add that here, but I didn't say it before. So you probably know that. What is the average? So the good news is, on average, we also get log 2 of n. Okay, and then we can talk about individual nodes as well, right? What is the depth of a particular node? What is its distance from the root? So here we have an example of a binary search tree. Again, take a node like this one, right? 36 is bigger, so it's to the right. 20 is smaller, so it's to the left. All right, so we do our analysis on the binary search tree, and I'm gonna wanna update this. So what's the worst case? So it means that insertions will always be proportional to the size of the tree. So what's the worst case for the first insertion? Let's say we have a root already. So it's going to be 1. Well, I guess the first one, there's no traversal that's happening. So you got 1 plus 2 plus 3, ... The last one is going to be n minus 1. So how much work? Okay, so that's O of n. What about in the average? So it's going to be log of 1 plus log of 2 plus log of, by the way, what does LG mean? What does LG stand for without the O in between? So it's related to log. I keep calling it log, but it's not just any old log. What does LG stand for?
Base 10 log.
No, I mean, I guess it's sort of arbitrary what we want it to mean, but what's the convention? So the convention is it stands for log base 2. Okay, so computer scientists use LG because it's short for log base 2. It's easier than having to write those subscripts, right? So that's the same as LG of n factorial, or it's going to be bounded above by n log n. And we've seen this before. You know where we saw this? Something like this. We saw it in the decision tree model. Okay, so the decision tree model for comparison-based sorts, we did something like these. Okay, so what about the worst case? I'm sorry, I got a mistake there. That's better. Okay, so the worst case, okay. And let me just be more clear what we mean here of n elements, right? So when we build a tree, we're doing n elements. And here we're going to just focus on a single element of a single. Okay, so what's the worst case? I have to go all the way down to the bottom, right? So that's going to be O of n. So we'll say n minus 1 comparisons for O of n. And what about the average case? All right. Okay. So what's your opinion of these binary search trees? You think they're good? So.
Well, you're also doing
Okay.
insertion.
Go ahead. Go
Well,
ahead.
you could also make it like a complete binary tree, right? Every time you do insertion, you have to insert it and make it complete. In which case, the search should always be O of log n, right?
Yes. So if you played with the binary search tree concept a little bit, so you could say that it's going to be complete. Okay, right? So nice and balanced, and you'll just have a few things that are at a different level at the end, the rightmost. But what's the drawback? So there's always a cost-benefit analysis. So what's the cost? So you've explained the benefit. What's the cost there?
Inserting, I think even the average would be n squared.
Right. So you're gonna have to do more work to insert, right? You may need to move things around. So what happens if you get a lot of smaller numbers? The root happens to be very big. You get a lot of smaller numbers. So, just inserting it to the left isn't going to work. You're going to have to shift things around, or what we call a rotation. So that's exactly what, most of the rest of the lecture is about is, what things can I do to compensate that, to try to get a more balanced tree. But before we go on to that, we'll talk about a few traversal algorithms. So the one traversal algorithm we already mentioned in this class was an in-order traversal. An in-order traversal means we recursively call in order on the left subtree, then we visit or print out the root, the key at the root, and then we perform in order on the right subtree. Does anyone remember where we mentioned that? We didn't spend a lot of time on it, but where did that come up? So it came up when we were talking about sorting, right? And we said that binary search tree, you can use binary search tree to sort in a way that's very similar to quicksort, right? Because a A node is basically like a pivot. It's like a partition, right? Left is smaller, right is larger. And we said if I do an in order on the binary search tree, I will get the numbers now in sorted order. There are other traversals, okay? So there's something called pre-order, which you do the root first. That's what's called pre-order. Then you do pre-order on the left, and then you do pre-order on the right. You have post-order, where the root goes at the end. That's what's called post-order. Post-order on the left, post-order on the right. And we do reverse order. First order, we do reverse order of the right, then we do the root, and we do reverse order of the left. And finally, we have, these are not the only options, but these are the most standard ones, level order, where you do things in increasing order from the root. So start you do the root, then it's children, then it's children's children, and so on and so forth. And it's basically like a breadth first search. What is the time complexity of these algorithms if they are implemented correctly?
O of n?
They are O of n, right? So if they're done right, okay, they should be, they should work in O of n time, because basically you visit a node and you shouldn't have to visit it again. All right, as we mentioned before, there is a binary search tree quicksort connection, right? So the root behaves like the pivot. We partition them into the small ones on the left, large ones on the right, and then we can use an in-order traversal. All right, so that's just to link what we're talking about today back to our unit on sorting. So now we get into what we call self-balancing binary search trees. That is a misnomer, all right? The search tree doesn't balance itself. The search tree does what we tell it to do, right? So we have to code for it. It doesn't happen by itself, but it means that it's built into the concept of the data structure. The code will provide for that. So there are different versions of this, how we get that balancing. Again, the goal is to be able to do this search, to be able to do these lookups in order of log n time, okay, as opposed to the worst case of n. We don't like that worst case. And again, it's not just about the data structure itself. So many things we're going to do later on in the semester. We're going to have a lecture on approximation algorithms, and we're going to look at something called the bin packing problem. And for the bin packing problem, we need something like a binary search tree. And we're going to see that the time complexity is going to be n squared if we use a regular binary search tree. But if we use one of these self-balancing trees, like an AVL tree, for example, then we can do it in n log n, right? Log n for each of the n operations. Okay, so why is it called an AVL tree? AVL has nothing to do with what it looks like. It's named after the two mathematicians, Russian mathematicians who made it. One of them is Adolf Svenvelsky, so that's the AV, and the other guy is Landis, and that's where the AVL tree. So the basic idea is that the left and the right subtree may differ at most by at most one. Okay, so it doesn't say whether the left subtree is going to have more nodes or bigger nodes, higher depth, or it's going to be in the right subtree. That doesn't specify, but the difference between the left and the right is going to be at most one. And we actually store that information. So in addition to storing the key in a node, in addition to storing any other values that are associated with the key in the node, we also store this information, which is what is the difference between the left and the right. Why do we do that? Why are we wasting space storing that information in the node? Right, so we're just increasing the space complexity, right? Remember what space complexity is. It's where I allocate space for information that's not part of the data. So the space that I allocate to the key, that's not space complexity. That's just the data itself, right? If I have values, that's just part of the data. But this is, introducing space complexity. So why am I storing that information in the node, this +1, -1, or 0? Well, let me ask it differently. Let's say it didn't store the plus, minus. How would I figure that out? How would I figure out the difference between the height of the subtree on the left and the right? I could do it.
Calculate both of them and then.
I would have to calculate both of them. So now, depending on what those subtrees are, that's a lot of work, right? Just to determine whether I need to worry about whether I need to shift things around. Okay, so if I store things, that will save time. So in database, I don't know if you've taken a course in database, that's an old debate, which is, do I store things in a database that I can compute? So one of the issues there is if something else changes and it's dependent, that's dependent on its now will change. For example, do I store someone's age if I already have their birthday, right? So if I have their birthday, I can always compute their age. So should I store their age? But a lot of databases store someone's age. Why? Because they need the age so frequently that it's worthwhile to store it. And then they just have to be careful to update it on some kind of basis so that it's current, right? So here it's very important to store that, because to determine the height using, let's say, that recursive function I showed you before would be bad. Okay, so how do we keep it balanced? So all of these use what's called a rotation, which is if I determine that either the tree itself or one of the subtrees is getting out of whack, it's getting unbalanced, so then I move things around, right? Just like has anyone here been on an airplane where they took people from one side of the airplane and moved them to the other side? It's happened to me. That ever happened? If you ride on like a small airplane, so sometimes they'll say, okay, you were supposed to be in seat 13, you're going to be moved to seat 16 because we need more weight on the right side of the plane, balance it out. So it's a little eerie when that happens. It's like, is it really that sensitive? Is this plane going to get there? Usually it works out, most of the time. Okay. So that's a self-balancing airplane, except the stewardesses have to balance it for you. Okay. Let's move on there. So here we have an example of the AVL tree. So we don't have any values here. We do have keys. And in addition to the keys, we have that little flag that tells us whether the left side or the right side is bigger, right? So you see that +1 there. That +1 means that the depth of the right subtree is, or the height of the right subtree is bigger by 1 than the height of the left subtree. Okay, so it's important that as you shift things around, well, first of all, as you insert things, right? So let's say I inserted the letter H here. What numbers would need it to be updated?
F would have to be 0, and J would have to be 0, and G would have to be 1.
Okay, so so the F would go to 0 because its subtree is now the same. The G would become 1. And which other one did you say?
I said the J was 0. You might be wrong now that I'm thinking of it.
So the J does not change, right? That's actually what I was after. J doesn't change because the subtree had a height of 2 before, and it still has a height of 2, so that doesn't change. But you're right, F does change, and the G does change. Okay, so you gotta update those. All right, so then we have something called a red-black tree. Okay, so here we're using colors to help us. Okay, so the red-black tree looks something like this. All right. Don't ask me why they have square nodes. Other pictures have round nodes. I don't know. It's a style thing. Okay, so they're either red or black. All right, the root of the tree is black. All right, there are no 2 adjacent red nodes. Okay, by the way, you can have adjacent black nodes, right? So it's not true that you can't have 2 adjacent things. And then we have the same number of black nodes as we go to the null, which is the bottom, the leaves. Okay. Right, and finally the leaves need to be black nodes as well. So again, what it does is we're using the colors to indicate where you have too many things close to each other. And later on in the course, when we talk about the graph coloring, we're going to do something similar to this. And you know where else this comes up? We do something called a bipartite. I don't know if you know what a bipartite graph is. but you can use a coloring technique to help determine whether it's a bipartite graph. So this coloring mechanism is used in various contexts for graph algorithms and tree algorithms. Right, now we have something called a B tree, and we have something called a B plus tree. All right, so what do you see about the tree that is different than B? Does not stand for, it probably does not stand for binary. No one really knows exactly what the B stands for. I think there was something called an A tree, so maybe the B tree is not the AVL tree. Maybe it's related to that. I think one of the authors, one of the designers of this tree had a B in his name. It's not, we're not really sure where the B tree, the B in the B tree name came from. But what do you see here that is different than what we had before?
I mean, each node can potentially have more than 2 children. That's just a regular tree, doesn't necessarily be it.
Okay, so what we see here is the node can have multiple children, and then we can, depending on where it is in that range. All right, so that's B tree. Now we have a B plus tree, and in the B plus tree, something, okay, so aside from the number of children, we'll talk more about that. There's some other interesting things that are going on here. So first of all, where are the pointers? Right, so the pointers in this B tree are basically following the usual rules of pointers. What about here?
They're pointing to a disk file.
So aside, well, okay, right. So we'll come back to that in a moment. So just in terms of the guts of the tree, right? So aside from the traditional, pointer to the left and pointer to the right, we can also go to siblings, right? You see that? We have siblings, right? So we're not necessarily going from parent to child, but we can also go from one child to the next child on the same level, and even spanning, we can even go to cousins. See that, right? We're even going to cousins within the same level. But as you just mentioned, right, there's something else here, which is where is the data? Right, so over here, right, you put stuff anywhere. Over here, the data is not even in the leaf nodes, right? It's in a completely different place. All right. By the way, anyone know where we use B plus trees? They're very popular in a particular context. And I'll talk about the, yeah, well, yeah, so the storage is on the disk drive, but in what context do we usually, we tend to structure our data using a B plus tree?
Merge sort?
Merge sort, maybe external merge, but not the merge sort we did in our class, no. Or first of all, merge sort, we're usually dealing with keys, right? We haven't spoken so much about having values, right? So just to be clear, we're talking about here is where we don't just have keys, we have values. So we're keeping the data itself not in the nodes, which is what you would typically do in a binary search tree, but we're offloading that, right? It's not even on the leaf nodes. So you know where we use this? We use this in databases. Maybe you haven't taken a course in databases yet. What is that 331? Which course is database?
Yeah, it's 331.
Yeah, someone in one of my classes this semester, I'm guessing it's not 220, so it's either 323 or 355. They handed something in and they put 331. So I guess they were thinking database. It was the assignment for our course. I mean, the course that I'm teaching, but it said 331. So I'm not sure exactly how that happened. Okay, so anyone know where we would use a B plus tree in a database context? Even if you haven't taken. So here's the thing, right? So in a relational database, what do you have? You have rows of data, right? And you want to search for something. So what do? So are the rows necessarily sorted? No. Even if you sort them, let's say they're sorted by last name, you could do that. It's called a clustered index. right? Let's say it's sorted like that. But what happens if I want to find something by first name? So now it's not sorted by the first name, it's sorted by the last name. So what do I do? Is anyone here taking database course? Well, so Cheng is saying primary key, right? So the primary key will often be sorted, right? Whatever the primary key is, it'll be sorted by that. But what happens if I want to look by something else? So the primary key is a social security number, but I want to look up by last name. I want to look up by first name. I want to look up by zip code. So how do I find that? So the answer is an index. Okay, and so I will actually need multiple indexes. I need indexes on anything that I am likely to sort by, and the database management systems will even tell you, you can use their diagnostic tools, and they will recommend that you create indexes on certain fields based on your search patterns. Let's say you're using what's called a table scan to find something. That's not very good. It's like O of N in our terminology, right? But it's worse than O of N. Let me tell you why. Because when you're dealing with something in memory, it goes very quickly. When you're dealing with something in main memory, when you're dealing with something in secondary memory, right, which is like a disk or a tape, right, it's really slow to get information off of that and then process it. So we really want to know where on the disk drive something is before we get it, right? Because it's a pain in the neck, right? It's sort of like, if I want to look for something in a book. So what do? I go to the library and I take out the book and I bring it home and I say, you know what, it's not in that book. So I go to the library again, take out a book, bring home the book, and I look in the book, and I can't do it there either. So why am I bringing it home? Because I'm not allowed to read the book in the library. It's COVID. I'm not allowed to sit there and read. Similarly, in a computer, it's not a COVID issue, right? But the secondary memory doesn't have brains. It doesn't have computing processing power. That happens in main memory. So I have to load it into main memory to do it. So you understand the back and forth, that's a pain in the neck. So we have the same issue in a computer. So we need very good indexing. B plus tree is very good index, but where is the actual data? The data sits on the hard drive because I have too much data. I can't store the database in main memory, not a big database anyway, right? So this is a commonly used in database. So great, so I have some differences, okay? So let's just run through these differences together, okay? So difference number one, right? All internal on leaf nodes have data pointers, right? I can store the data at any place in a B plus tree where the leaf node, where the data pointers and the leaf nodes. Leaf nodes means on the bottom of the tree. Okay, search, since all keys are not available at leaf, right? Search often takes more time. Okay, all the keys are at leaf nodes. Okay, so it means I always have to go to the bottom to get it, which may actually take more time. So it's a little misleading, but at least I know where I'm going to find it, and they tend to be flatter. So that's actually where you get the speed from. Okay, redundant keys. So in a B plus tree, you can have that. Keep in mind that that's very common in a database, right? So if I'm searching for something with a, let's say a particular first name. So in our classes this summer at Queens College, we have people with the same first name, people with the same last name. So if I'm storing records for them, it could happen that we have duplicates of certain things. Okay, insertion takes more time. Insertion is again, it's more consistent because I know what the height of my tree is. All right, I don't really want to talk about deletion today. So here's another thing that's interesting, right? We have the structured linked list. Okay, I'm able to go from one node to the next across a layer, right? So that also enables us to have sequential access. All right, that's another difference between the B tree and the B plus tree. And then we have the applications. Okay, so they're both used for database, but the difference is this is used for actual indexing, this is used for the actual storage of the data. All right, so here's another thing. Okay, so in the intermediate level, you have at most 2 nodes, and here you could have many nodes. And notice that the number is variable. Okay, so we do have this is also interesting, we didn't say before, so I'm going to say it now. There is a lower bound So one of the problems with the binary search tree is no one, sometimes I'm only using one node, sometimes I'm using, well, at a leaf I have 0, but in a B plus tree, I have to have at least n over 2. N is misleading here. N should really be m children, right? So if I'm allowed to have up to m children, then I have to have at least m divided by 2, because otherwise I'm not efficiently making use of my data structure. All right, we're going to move on to another tree structure, and it's guided by the following. Okay, this is particularly for strings. All right, let's take, you'll appreciate this more with an example, okay? So let's say I am looking for the name David in a binary search tree that looks like this. Everyone see that this is a binary search tree, right? How would I find David? What would I do?
Start at Dawn and then see if David is earlier.
Okay, so I compare David to Dawn, and I determine that it's less than Dawn, so I go to the left, and then I'm going to compare it to Dave. But before I do that, how do I compare David to Dawn?
And normal is to take the values of each subsequent letter.
Okay, so I need to compare the D to the D. I determine they're the same, so I move on to the next letter. I compare the A to the A and determine they're the same letter. I compare the W to the V, and now I have a determination, right? So when we compare strings, if you're in Java, if you're in Python, you can just say less than. And if you're in Java, you'll use a compare to. So we think of the compare to as, a one-step operation, but it really needs to compare character by character. So we need 3 character comparisons to determine that David is less than Dawn, at which point we can move to the left. Okay, then we do the same thing. We compare the D with the D, the A with the A, the V with the V, and those are all the same. Then we compare the I with the E, and we determine that the I is greater than the E, so we go to the right, and lo and behold, and then we do the same thing again, right? We're looking for David. So we compare the D with the D, and the A with the A, and the V with the V, and the I with the I, and the D with the D. They match. We found David, and then whatever information we want to have about David is there. It could be it's the wrong David. Then there might be another David in this tree. All right. So anyone see a sort of problem with this this approach? I mean, it's an approach we use. Certainly, binary search trees are used for strings, but what's the problem with it? The string is too long. Well, we can't control the length of the string, really, right? I mean, Dawn is Dawn, and Dave is Dave, and David is David. So what are you saying there, Cheng? Let me just see. So it's gonna take time to compare, and it's gonna make a lot of time to compare, right? So what's bothersome about this?
You have to compare each letter individually instead of all at
We're
once.
comparing, but yeah, I don't know how much control we have over that. The problem is we're doing the same thing multiple times. That's what it really boils down to, right? So if we need to compare David to Dawn letter by letter, that's what it takes, because we don't have any magical way to, do the whole thing at once. Then that's what we have to do. But we're comparing D with D, and then we're comparing D with D again, or comparing A with A again, and multiple times, right? So the idea would be if we could, once we know that D is, the same as D, if we could utilize that information to get us closer to the result, right, that would be nice. Okay, so another way of saying it is what we said on the previous slide. So now I'm going to go back to the previous slide so you can appreciate what we're saying. Right, what we're saying is the search hit takes time proportional to search key length. Meaning, if I have 5 characters, I should not do more than 5 comparisons to determine that I got it. And if if it's a miss, they don't match, then I should know that it's not there with at most the number of characters, and hopefully less, right? So that's where we get something called a trie, okay? It's called a trie, which is interesting because it's from the word retrieval. So really it should be called a tree, but why do they not call it a tree? Because a tree is a generic term for all kinds of different things, okay? By the way, it dates back. This is pretty remarkable. First of all, that's earlier than the AVL tree that we talked about earlier today, right? It's earlier than a lot of the algorithms that we're studying in this class, including the old ones like the Karatsuba algorithm, right? So that's pretty early on in terms of the history of computer science, right? So what is it? Well, we're going to see in a moment. Okay, so how are we finding a word here, right? We're no longer storing entire words in the nodes. What are we storing in a word, in a node? A non-leaf node, what we call an internal vertex.
A letter?
A letter. Okay, and the way to interpret this tree, it is a tree, it's a trie, but it's also a tree, is the way you get a word is you navigate from the root, to the leaf, and that will get you the whole word, right? So this is, instead of having a bull here, you get bull by going all the way down to here. When you get by, you got to take, the path from the roots and you navigate, and the B from that node and the U from here and the Y from there gets us by, right? So what's the advantage to this? Well, if I go back to the other example with the Dave or David, right, I would have a D here, and then an A here, and then a V here, and then a I there, and then a D there. And each level takes one comparison for one character. And once they hit, 5 comparisons, I will have my David, right? I'm not, comparing David against, what was that other name there? Dawn, right? I'm not comparing David to Dawn and then comparing David to Dave, and then finally the David to the David. All right. So now the amount of work it takes is proportional to the character. It's to the length of the word, right? The length of the word determines how far it is, its depth in tree terminology. Does anyone see a drawback? Okay, so this is a very nice idea, and it's used. It's used, in where appropriate. But there is a drawback here. All right, so my favorite answer is it depends, right? So is this good? It depends. What's the drawback? So let me drill down, no pun intended here. All right, how many, if you were implementing this, so we have a nice little picture here, but if you were implementing this, can you describe, if you could even write it into the chat if you like, what would the data structure for one node look like? Either talk or write in the chat, whichever you prefer. So for all the nodes, right, they're going to have, a data structure. So when you implement a binary search tree, you have a node data structure, and then the node data structure has a pointer or 2 pointers, right? Left child and right child. If it's a ternary tree, it'll have 3 pointers: left child, right child, middle child. Some will be null, some will be filled. So what would the data structure for one node look like in this tree?
You would have data and a list of children.
Okay, so you would have your key. The good news is you wouldn't actually have the data itself, because the data itself is only for the leaves. So you would actually probably have 2 data structures, right? One for a leaf node, also known as an external vertex or a terminal vertex, and you would have another one for the internal vertices. Okay, so the external ones would need to have room for the data itself, the value, if you like. But you said something about the children. So can you be more specific about that? How would you store the positions for the children?
I mean, in some sort of ordered list.
Okay, so it'd be a list. And can you comment on the size of that?
Variable, since they could have a change in amount of their children.
Okay, that's a fair point. So one idea would be, and you're already getting to the plan B. One idea would be, let's go back to a binary search tree for a second. So how many children can a binary search tree, a node have?
2 at most.
2. And when you create a node, for a binary search tree. I'm imagining you all did that at some point in your data structures class, right? So did you use a, let's say like a linked list for the children, or did you do something else?
No, we just had 2 pointers, like a right and left
You
pointer.
had 2 pointers, right? Even though you know fully well that if it's a leaf node, it's going to use none of those pointers. It's just going to put null. And if it's somewhere else, it could use 1 or 2. But you probably had 2 pointers, you know, one called left and one called right or something like that. Okay. What about if you're doing a ternary tree? So I don't know, you might not have implemented a ternary tree in data structures, but what would you do there?
I mean, you could add like a list of 3 pointers or make 3 individual.
Right. So you would probably have 3 pointers, right? Left, right, middle. We'd probably do that. Now, what you're getting at is, yeah, but you know, what happens if it's a ternary tree? If it's a ternary tree, you really want to have 10 pointers. So the way this is designed is really you're supposed to have 26 pointers, and that's assuming it's not case sensitive, which for this kind of purpose, it doesn't need to be case sensitive, right? You would have, 26 pointers representing the different letters that are possible. Okay, what's the problem with that? So the fact that you mention a linked list means you're already sensitive to what the problem is. What's the problem with having 26 pointers for each possible letter that's a child?
Oh, it just gets really hard to handle.
It's actually not hard to handle. It's just big. It's actually easy to handle, right?
I mean, code-wise, it gets really complicated if there are 26 comparisons each time.
Well, yeah, okay. So you gotta figure out, you know, which child it's going to be. Okay, so fine. So use a linked list, and that way it's also a space complexity issue, right? Because you got all these pointers that you're not going to use, right? There aren't too many words that begin with BZ or BX or BQ, right? So do I really need a Q placeholder? I'm probably not going to get any words that begin with BQ. Okay, so, all right, you suggest an alternative. Well, if I don't know how many children I need, so I use a linked list. What's the problem with the linked list? So what happens if,
Fourth element, you got to go to the first 3.
what happens? Okay, so first of all, if it's a sequential list, to get to the last one, I have to go through the whole linked list. That's one problem. The other problem is what happens if I want to insert something? Okay, so now I have to move them around. So you'll say, well, linked list, I just splice in the node. But remember, from a memory management perspective, linked lists are bad. Okay, why is that? Can anyone tell me why from a memory management perspective? So in data structures, you don't necessarily worry about that. You worry about, just a code perspective. But from a memory management perspective, why are linked lists bad?
And you have to hold the and the pointer, so it's like extra data to hold.
Well, the problem is that your stuff gets scattered all over the place. So, imagine, you go look for something in the kitchen. So in the kitchen, it says, okay, if you need that, go down to the basement. It'll tell you. Have you ever done a scavenger hunt? Anyone here do a scavenger hunt where it gives you a clue where to look, and then you go find that clue, and the clue tells you to go to another clue. And to get to what you really want, you got to go through all these different steps. So that's the problem with the linked list in memory, right? It looks very nice in the code, right? It's just a pointer, but you have to jump all around different parts of memory, and that memory maybe is as external storage, secondary storage, which is slow. So you're going all over the place. It's nice to have your stuff contiguous in memory, okay? So if I allocate my 26 possible pointers, they will be contiguous in memory. Yes, some of them are going to get wasted. So that's the pros and cons that we have here. All right, so here is the node representation for a trie. So notice we have a lot of placeholders. Why do we have so many placeholders? Because we need to have a position for each possible character. All right, notice on the very bottom there, I hope you can see it on your end, it says R equals 26. So R is basically referring to the size of these pointers, right? There are 26 children representing the 26 possible letters. But that has its drawback, okay? We have something called a quad tree, okay? What do you think a quad tree is? Before we get to what it's used for.
It's for children.
It's got 4 children, right? I was trying to look up the name. I think it's called a quaternary tree if it's just 4 children, but a quad tree is more complicated than just 4 children, right? It's not just a 4-area tree, right? It's used for dividing up a space, particularly, like a geometric space, right? So you can think of it in quadrants, right? It's often used for representing, let's say, maps or, geography or even farming, right? So you may have, in this corner, I think I have a picture of that here. Right. So, you take your area and you break it up. Okay. So this area is going to be forest, right? Just trees. This area I'm growing certain kinds of crops, right? So you keep on breaking it down and you can divide it that way. Okay. So it's used for geographical kind of mapping, right? Where each direction, it becomes a sub kind of area. What do they call it? They call it geospatial. That's the term they use, geospatial, right? So again, it's like a specialized data structure, depending on what you want. By the way, today, databases are designed, to take into account all these, because we do that a lot, right? All these maps. Think about, let's say, like a Google map or any other map, right? Where you click on something and it drills down and it gives you the next level of detail. So this kind of data structure might be relevant there. So notice what we're doing here, right? In this abstraction, we're taking this region. It's not a Sudoku puzzle, by the way, right? So we're breaking it up into 4 regions, and then each of the regions is broken up into 4 regions, and so on. Okay, all right, so let's take a look at this. So we're back to our Find the Binary Search Tree. We're not going to go review everything about binary search tree again, but the reason we're doing that is because we have a randomized binary search tree. So I think this is our first randomized data structure. Is that maybe not? Did we? So we had a bunch of randomized algorithms. Anyone remember a randomized data structure? I think I mentioned very briefly. We're talking about lists. We talk about skip lists. I think we mentioned very quickly in passing, right? So your traditional, typical linked list, how does that work?
You have data and then a pointer to the next element in the list.
You have a pointer to the next element, and from that element to the element after that. If it's doubly linked, you can go from the right end to the one before it, and so on and so forth. Okay, what's the problem with a singly or doubly linked list?
It takes a little bit to get to.
So to get to the middle, you got to go one at a time from one end, or if it's doubly linked, one end or the other. And it would be nice if we could jump around, right? So there is something called a skip list, which enables you to jump, so it's just like, let's say, you have a big highway, right? You have a big highway. So every once in a while, there's a place where, so if you want to get to the other side, what do you need to do? What you need to do, you need to drive down to one end, get to the other side, and then come back up. But it's nice every once in a while, there's an overpass where I can get to the other side quickly, right? So a skip list says I can skip, I can jump from one node to a lot of nodes forward, and then I'm going to be closer to where I need to be, right? So we call that a skip list. Now, what are those jumps? What sizes? So there are different strategies for that. One strategy is to use a random number to determine, how big the jumps should be. So that's an example of a randomized data structure. So here we have an example of a randomized binary search tree, and we have a name for that. I'm not sure exactly what the origin of the name. Obviously, tree sounds something like a tree. I'm not sure where the other piece of that name came from. Oh, you know what it is? Because it's a little bit like a heap. Okay, so we're gonna see that in a moment. Okay, so if you take a look at this picture here. Okay, so we have two values in each node. Okay, one value is green and the other value is light blue. I don't know if you can, hopefully you can see that on your end. Right, the green ones are the ones on the top of each node and the light blue ones are on the bottom. So can anyone look at that first picture there? And someone tell me what is the pattern among the green?
It's in a decreasing order.
What's
Like the-
decreasing? The green
The
ones.
left, like on the left, it's decreasing, and on the right, it's increasing.
Okay, there we go, right? So on the left, it's decreasing, and on the right, it's increasing, and that's similar to what that we've seen before. Where have we seen that kind of concept before today?
Just binary tree.
Binary search tree, right? Binary tree doesn't have any ordering to it necessarily, but yes, a binary search tree follows that property. Okay, good. Now, I want you to look at the blue. So ignore the green for a moment and look at the blue. Do you see any, pattern, property among the blue?
Seems random.
They're what?
Seems random. No. I mean, like the bigger
okay,
one
so
on the top.
So they happen to be assigned random, so that's why this slide is in tree, randomized binary search tree, but there's a pattern. Thank you, Samuel. So Samuel points out that there is a heap pattern here, not just a heap, but a max heap. Everyone see that? The parent is bigger than the two children. So we've got, this is an interesting hybrid. That's why they call it a tree, right? It's a combination, a hybrid, if you like, of a tree, of a binary search tree, and a heap. So what we're doing is we assign random numbers to, you'll have to pick what range to use, but you assign random numbers to the nodes as they get inserted. And then we have to preserve the heap property as well. Okay, so let's look at this example here, okay? So we are inserting an 80, right? Where does 80 go from a green perspective, from a binary search tree perspective? Where does the green need to go?
On the right side.
It needs to go on the right side, right, of 70. Okay, it goes there, and it's assigned a random number, okay? So again, I don't know what range it's coming from, but somehow it landed up with the random number 12, right? What's the problem with our data structure right now? So Samuel, can you answer that? I'm asking you for a reason. Why am I asking Samuel this question?
It's no longer following the max heap structure.
Okay, thank you, right? It's no longer following the max heap structure. What do I need to do? I'm going to need to put the 12 higher up and the 10 lower down. So we do a rotation to preserve the heap, or restore. That's the word we like to use, to restore the heap property. Okay, so that's what we're going to do. All right, so we use the random numbers to sort of manage this situation. Then we have some rotation. So again, the details of all these things, the code behind all the rotations are not in the slides. You can Google them. I'm trying to introduce you to a lot of different approaches. And then again, whether it's for the for the next assignment, or just in general, if you find that you need to do something, you are aware that it's out there, and then you can look it up. Okay, let's all right, so we're now going to move on to some kinds of heaps. But before we get to the heaps, we have a concept of a disjoint set forest. All right, so earlier today, when we talked about some special trees, I said there's something called a forest. I said it's not really a tree, it's a set of trees. and they are disjoint. Okay, so everyone see that? We have a bunch of trees. Now you'll see a double arrow here. Okay, the double arrow is basically saying that these two trees are merging. Okay, what happens when the two trees merge? Well, how many roots are they going to have?
They start with one, but they have to get down to two.
I'm saying we started with 2 roots, right? Because we have 2 trees that are merging. And how many do they go down to?
One. Yeah, sorry, I said that backwards.
1, right? It's sort of like, let's say you have 2 companies, right? 2 companies merge, and generally speaking, the people who work for one company don't work for the other. So we could say they're disjoint. There are cases, where someone's actually employed by 2 companies, but let's assume not. So they merge, and you're going to have a new corporate hierarchy, right? New corporate structure. Generally speaking, there's going to be someone at the top. Sometimes they call them the CEO, sometimes they call them the president. Sometimes they have 2 people at the top. And that can sometimes be a little messy, right? Okay, so who's the boss, the president or the CEO or the chairman of the board, right? So it gets a little tricky, who calls the shots. But in any case, for the purpose of data structure, we get 1 root. So there's a whole, the whole discussion, a whole science around how you merge these 2 trees, who becomes the root, and what happens, how does the subtree fit in to the new structure. Anyone know what we call that? We have a name for it. It doesn't appear on the slide. I believe there's an entire chapter on it in the ZyBook. I don't know if anyone, some of you have been a little aggressive with the ZyBook. That's good. Don't save it up. So there's a whole chapter on this in the ZyBook. And if it helps at all, we will be talking about it again when we do Kruskal's algorithm later on in the semester in minimum spanning trees. So it's called union find, or they call it union find, but it's really find union, okay? Because what you usually do is you find, and then in some cases you then do a union. Okay, what do I mean by that? So you might say, okay, the 2 and the 5 now need to be in the same tree. Okay, so first I find the 2, I determine it's in this tree. Then I find the 5 and I determine it's in this tree. And then we merge them, we do a union, and that's called union find. Okay, so we'll come back to that later on in the semester. But that's a pair of operations that is used for disjoint sets. It's usually a third operation. There's make set, which makes a component or one of these little trees for an item. Then we find where 2 items are and we combine them and we call that union. Right, so this is a disjoint set forest. Right, another data structure that is can be important is something called a Fibonacci heap. It's called a Fibonacci. It's called a Fibonacci heap. Okay, why is it called Fibonacci heap? No one here is in my 220, but you all know about Fibonacci numbers. What do you know about Fibonacci numbers?
It's always the last 2 elements added together, starting with 1.
Right, so each term is equal to the previous 2 terms. So Fibonacci did not make this heap. He did not design this heap. I don't know if there was such a thing as a heap back in his day, but the analysis of the Fibonacci heaps turns out to use Fibonacci numbers. So what we're doing here is this is a kind of forest, if you like. Okay. It's a heap. I don't know if you can tell that. So each of these trees is a heap, and now we're merging them. So it's a way of doing it, but now we sort of can have possible multiple roots along a line. Okay, so it's a specialized kind of data structure. The beauty of this Fibonacci heap and the binomial heap. Anyone know what binomial is? If you took probability, or maybe it even came up in discrete structures or discrete math. So binomial are those, that's like the C and R, right? How many ways can you choose R from N? So again, it's called the binomial heap because the math that's related to its analysis uses those binomials, right? So they're both it's like a heap forest. It's a bunch of heaps. And the reason they're valuable is they have very good time. More specifically, they have something called amortized time, which means any given operation may take a little more or a little less, but if you sort of add up all the work you're going to do, it's not exactly the same as an average case. It's saying you look at the total work that you will be doing. It's not, what may happen. Total work you will be doing over the course of things, it adds up to a amount that is sort of near linear. Okay, so that's really an ideal. Okay, so these are some sort of advanced heap structures, and we will be revisiting them later on in the course. Okay, so let's see how we're doing on time. So we do have about 20 minutes left. So what I wanted to do now, nothing related to the first part of the lecture, but something that is important for this class. So I'm going to bring it up. I guess I can share my screen again. Yeah, I needed to escape. That's what I need to do here. Okay. So lecture slides. Okay, so you can be pretty sure there's going to be a recurrence equation on your final exam. So what I wanted to do with you, since we have some time today, is to walk through a problem and a solution from an old exam. Okay, and as you can see, I put some effort into writing out the solutions, so it's as clear as possible, but I do want to walk through it with you. Okay, so again, one question you can be pretty assured of is there'll be some kind of recurrence equation on the exam. Okay, so let's take a look at this recurrence over here. All right, what kind of algorithm, by the way, would have a recurrence like this? So we've done a lot of different kinds of algorithms at this point.
Closest point algorithm.
A which kind?
Closest point.
Closest point. So I don't think we had those exact numbers in closest point. We did have recurrences that look sort of like that, but I don't think we divided it into thirds. But more generally, what would this kind of structure, what kind of strategy?
That's a divide and conquer strategy.
That's a divide and conquer, right? So more specifically, we would say we're dividing something into 3 subproblems, right? And somehow, even though we only have 3 subproblems, we land up having to do 4 subproblems, 1/3 of the size of the original. Okay, and then we have the n. What does the n represent? The n represents either the work to divide the subproblem, like in quicksort, there's a lot of work involved in dividing and partitioning, or it could be the work involved in putting the solutions together, like in merge sort. So you can't tell by looking at this where that n is coming from, and you don't need to for the purpose of this question, right? So we want to solve this. And before we solve it, we also are asked to begin by using the master theorem to predict the complexity class of the solution. Sometimes what happens is people, especially where we didn't have in-class finals, so everyone has a copy of the master theorem in front of them at home. They can Google it and they look it up, and they can usually, right, usually they know how to deal with the master theorem. Then they actually try to do the recurrence, and they get a completely different answer that's a different order of magnitude. All right. So that the whole point of the master theorem is to predict the complexity class, so you know what your answer should look like. You get a different answer, so then you know that something went wrong. All right, so let's use our master theorem here. So what is A in this case?
4.
A is 4, right? That's the number of subproblems. And what is B?
3.
3, right? That's the what fraction of the original size is the subproblem. And then what is C?
1.
And where did that 1 come from? I don't see a 1. It's not this.
Power of
The
n.
power of n.
It's the power of n, right? So the power of n, the degree of that polynomial, if you will, is 1. So we then use that comparison, right? So we take the log b of a is log 3 of 4, which is 1 point something. Okay. that is bigger than 1. So we use the rule of the master theorem that says that in that situation where the log BA is greater than C, our solution is going to be of the form n to the log 3 of 4. Again, the n to the log 3 of 4 is in the ballpark of 127. So that's n to the 127, right? So we're dealing with something that's between linear time and quadratic time, closer to the linear time. All right, so, yeah.
On the test, are we allowed to leave it as log 3/4, or do we have a calculator? Because I would never know.
Right, so you would not need to know in your head that log 3 of 4 is 127. You should know, if I asked you between what, major complexity classes, you should know that that's between 1 and 2. So that much I would expect you to be able to do in your head, but you would not need to know that that's 127.
Okay.
I don't expect that you will be able to use a calculator or any other devices. So that, creates inequity depending on what people have going on in their calculator. So assume it's a closed book, closed notes, no devices, okay? But, so you should know that log 3 of 4 is between 1 and 2, but I would not know how it, that it's 127. Guess if I worked at it, I could probably get to that eventually, but how would you do that? Not necessarily during an exam, but if you wanted to write a program and you weren't allowed to use the log function, how could you do that? That's actually something you could do. So think back to your our lecture on numerical algorithms. Let's say you were not allowed to use the log function. What could you do?
I mean, you get in the ballpark by knowing it's between like 1 and 2, because it's between 3 and 9.
All right, so you're the one that asked me the question about the estimate, right? When we did the binary search, was it the Babylonian, one of those, right? How do you get that initial estimate? So let's say you get your initial estimate. Now what do? You say, okay, well, let's assume that it's 1. Well, 1 is too small, 2 is too big, right? It's obviously 3 to the 2, right? 3 to the 2 would give you 9. So you say, okay, let's try 1.5, right? Then you determine 1.5 is too big. Then you go to 1.25. 1.25 is too small, right? So what do we call that? What do we call that approach that I just described?
Babylonian method? I mean,
that's not the Babylonian method. You might be able to use a Babylonian method, but that's not a Babylonian method. What is it? What method am I describing? We keep taking the average of the, the 2 endpoints.
Well, that was the binary search for?
That's a binary search, right? So binary search isn't only for, looking for a key in an array. It's a methodology that can be applied to many different things, right?
If I wouldn't know how to, on the test, I wouldn't know if 1.5 was too much or too little.
No, but I'm saying you could write the code to do it, right? You could write the code, even if you don't know what those numbers are going to be, you could write a simple while loop to figure out, and then, you give it an epsilon, where if it's close enough, again, I'm not asking you to get the numbers. Okay, but that's not really the point here. Okay, so what I really want to do is, how do you find a closed form formula? Okay, so the first thing you do is we need to set up a domain transformation. Okay, what does that mean? It means having this n divided by 3 is ugly. But if we assume that n is 3 to the k, and I'll talk about that assumption in a moment, which means that k is log 3 of n. So now I can rewrite this as a function of k, right? So what does that mean? It means t of n is s of k. So we're using instead of it being a function of n, we're saying it's a different name, and it's a function of k. And we're going to say that that's 4 times s of k minus 1. Does everyone understand why that's s of k minus 1? Why is that s of k minus 1? Because if I take n and divide by 3, that's the same as 3 to the k divided by 3. So that's like 3 to the k minus 1. So we're saying instead of it being, it's a function of k. So when it gets down to n over 3, that's like k minus 1. So what I'm doing is I'm substituting the 3 to the k for the n. 3 to the k divided by 3 is 3 to the k minus 1. So instead of t of 3 to the k minus 1, I have s of k minus 1. So we call that a domain transformation. Why do we call that? You had a little bit of that back in the slides for, I think it was lecture 3 is when we did the sorting. So I think it came up way back at the beginning. And then we can't forget about our base case, okay? So S of 0 is the same as T of 1. Why? Because I plug in K equals 0 and I get 1. So S of 0 is the same as T of 1, and T of 1 we're told is 2. Okay, so that's this. All right, so now okay, and then this was just an explanation for what's happening over there, right? So this line here is an explanation for what you're seeing in that line. Okay, now we're going to use a range transformation. So in functions, what do we mean by range? You have domain and range. What do those words mean, right? That's your CS or Math 120, as well as pre-calculus.
Of all possible inputs in the range of the set of all possible outputs.
The domain is like the possible inputs, and the range are the, the realized outputs. Okay, so we're changing not the input to the function, right? So notice our R of K, which is our range transformation, is still a function of K. We haven't changed the domain. But what are we changing? We're changing the output. So before we had this 4 there, we're saying we're going to divide that S of K by 4 to the K. Now, you say, why are we dividing by 4 to the K? Because you have to make it work. And the way we make it work is now when we divide S of K minus 1, where you got that 4 there, you divide by 4 to the K, it's going to get nice. Okay, what do I mean by that? So what happened to that 4? It falls out. Okay, so we try to figure out, when you do these recurrences, you try to figure out, I need to get it into a format that is going to work nicer. So first of all, dealing with K minus 1 is nicer than an N divided by 3. So we eliminate that. That's what the domain transformation does. And what I'd like you to do is, go home and then take this answer. This is now in our old exams directory. And probably have another example of this in the winter one, and you can look at that. All right, and walk through it and spend time on it. All right, so what we're doing here is we're saying divide through by 4 to the K. So what happens when I divide this by 4 to the K? That's what's doing here. The 4 over the 4 to the K is going to come out to be 4 to the K minus 1, right? The 4 is going to cancel one of these 4s. And now I have R to the K minus 1, because RK minus 1 is equal to S of K over K to the 4. All right, so, and then we do the base case here, right? So we say R of K is equal to S of, I should put a 0 here. Okay, which is the same as 2, right? We get the 2 there. And 4 to the 0 is 1, so we get a 2. And now what we do is we're going to write out these equations. And can anyone tell us what we're trying to do here? Why are we writing these out? What are we aiming to do? Where have we seen this before? I'll give you a look at the next line.
Telescoping.
Telescoping. And who remembers why telescoping is called telescoping? What does the big telescope do, right? It collapses. It collapses, right? So all the terms cancel out. So if we look at all these equations, right? The first equation is R of K minus 1 is 3/4 of the K. Next, if I plug in K minus 1, I get R of K minus 1. R of K minus 1 minus 1 is R of K minus 2, and 3/4 to the K minus 1. So if I write all these out and then I add up the left-hand sides and I add up the right-hand side, so what do I get? What do I get? Well, all these cancel out except for the first term here and the last term there. Okay, so that's what you see over here. This is after the telescoping, right? All those intermediate terms cancel out except for the first and the last. Okay, what happens on the right-hand side? We get what do we get? If I add up those terms, we call that a what from CS or Math 120? the right-hand side. It appears later on in this answer key. So I have 3/4 to the 1, plus 3/4 to the 2, plus 3/4 to the 3, plus 3/4 to the 4, plus 3/4 to the 5, etc. What do we call that? Give a name for that.
The series,
It's a series, and which series is it?
harmonic.
Not the harmonic. No, harmonic is 1/1 plus 1/2 plus 1/3 plus 1/4.
Geometric.
It is a geometric series. Okay, so on the left-hand side, we have this R of k minus R of 0, but we know what R of 0 is. We got it up there, so we're going to replace that with a 2. And on the right-hand side, we have a geometric series. The ratio of that geometric series is 3/4. And I goes from, or a J rather, J goes from 1 to K. The reason I don't use I, it's not that J is better or worse, is that Google Docs has a way of switching, and Microsoft Word has a way of switching lowercase i's to capitalized, because it thinks you mean I, like the pronoun. So I like to use J because it doesn't change the J's on me. Okay, so I have a geometric series, and down here I replace the geometric series with the formula. Just so you know what happened here, I took my 2 and I broke it up. I said one I'm going to keep there, and the other one I'm going to make it part of my geometric series, and that enabled me to change my index. Instead of going from 1 to K, it went from 0 to K, because 3/4 to the 0 is 1. So I get a geometric series, and then I work my way backwards. Okay, so here's my geometric series, and I just simplify all that. I get this, and then I work backwards. I say, well, okay, so I have R of k equals this, but S of k is equal to R of k times 4 to the k. All right, so where did that come from? It came from over here. Over here, right? S of k is equal to 4k times Rk. All right, so I work backwards. I take 4k times this, so I get 4k times the 5, and 4k times that, and I have a 4 on the bottom to the k plus 1, and that 4, and then I have another 4k, so those are going to cancel each other out, and I land up getting this, and finally I work backwards from the S of k to the T of n. So we know that T of n is equal to S of k, and I have 4 to the k. What is k though? K is log 3 of n. So I have 4 to the log 3 of n, which is the same as n to the log 3 of 4. And I get that. Okay, what's really cool about this is I've got all these logs going on, but all my numbers are always going to be integers. So if I test, right? So generally speaking, you want to test this. So I plug in 3, and I use my original recurrence, right? So I plug back into this recurrence, okay? What does that mean? I plug in 3 there, and I get 4 times 3 over 3 plus n. Well, T of 3 over 3 is 2, times 4 is 8, plus 3 is 11. That's where this 11 is coming from. And then I plug into the formula, and I get log 3 of 3. What is log 3 of 3?
1.
1. 4 to the 1 is
4.
4. 4 times 5 is
20.
20. Minus 3 times 3 is
9.
9 is 11. Okay, so there's a lot to absorb there. There is a lot to absorb there. A lot of techniques that we're using. We've got domain transformations, got range transformations. We have telescoping. We have geometric series. But I give you a very elaborate solution. So I want you to look at that. And
Professor, can you repeat the range transformation?
Yeah. Okay, so again, it's helpful to understand why it's called a range transformation, so you know how it's different than the domain transformation. The domain transformation
is like, where did you get the RK minus 1 from the?
Well, first you need to get the R of k. Once you have the R of k, then we get the R of k minus 1. Okay, so the range transformation says we're still dealing with a function of k, but we're going to change the range. The way we change the range is we say whatever you get for S of k, you divide by 4 to the k. Okay, then I say, well, what is S of k? If I look over here, S of k is 4 times S of k minus 1 plus 3 to the k. So I say, let's take that and divide by 4 to the k. So instead of dividing it by 4 to the k, I just wrote it this way. I say multiply by 1 over 4 to the k times whatever S of k is. And then I multiply that out. So I get, if you like, maybe I'll just introduce one, maybe this will help you. Okay, so if I do this.
Yeah, that's where I got confused.
I'm just going to add one more step there. Okay, so what do I get? I get, I'm going to distribute this out, right? So I have, okay, and then over here, okay, so you see, you see now, so that's where the 3/4 to the k comes from. And if I have 4 times S over k divided by 4 to the k, so that's equal to, I could introduce one more step if you like, if you think that's helpful. So we could do this. We could say that's equal to 4, the 4 comes out. Is that better? And we could write it like this. Say 3/4.
Oh, okay. I see.
Okay, I hate when it does that to you. Okay. So maybe with the extra steps there, it's a little better.
Yeah, now it's clear.
Okay, all right. So this is available to you, as are, have the winter for, I taught this in winter 2022, as well as a lot of old exams in the PDF. And some of them have solutions, some of them don't, but sort of get the hang of what's going on here, all right? So that is going to be it for today.
Professor,
Yes.
what's today's attendance code?
Oh, yes. What is today's attendance code? Someone have that handy? Otherwise, I can go look it up. Okay, thank you.
Thank you.